Okay, this is for lesson 2.1. This is for Mr. Fender's college algebra class that meets Tuesday, Thursday from 5 to 6:15. I do apologize for not being able to be in class today, but I'm going to get started with your fill in the blank notes, and then we will take a look at some things out of the book. The title of this section is Graphs of Basic Functions and Relations. We're also going to be talking about some symmetry. We're going to be discussing how we can describe certain graphs of functions. Sometimes we may come across some relations in addition to that, but let's just get into it. The first way we are going to describe a function is whether it is continuous or not continuous. It is said to be continuous if over an interval of whatever its domain is, even if it is from positive infinity to negative infinity. Over its entire domain, you can draw the graph without lifting your pencil from the paper. If you have to lift your pencil from the paper, it is not continuous. And there are two places where it will not be continuous at. It is either a point of discontinuity, which happens at a single particular x, the graph jumps to a different location, or there is something called a vertical asymptote. And an asymptote is a line. Vertical means it goes up and down, and that line, your graph will neither touch nor cross. So notes say see page 89, figure 1. On page 89, figure 1. That would be, sorry about that. My stand is a little off. I am. Alright, so figure 1 is right here. This is what we call the point of discontinuity, where at x is equal to 2, the graph jumps from this location up to here. There is a break in the graph. You have to pick up your pencil and move it to a new location before you can continue. In this particular example, you have this part of your function, this graph here. You have to pick up your pencil to get to this part of the function, but there is a vertical line at 2 that neither one of these graphs, parts of the graph, will ever touch or cross over. This is what we call a vertical asymptote. So here, for intervals, because this entire graph right here, which we call a parabola, you can go for the duration of the entire graph without ever picking up your pencil, no matter how far up these two arrows take you. It is going to be continuous over its entire domain, which goes from negative infinity to positive infinity. This graph right here, oh, there's a bubble right there. That means there is a point right here where x is 3, where it is not continuous. Okay, you have to pick your pencil up and go over that point to continue on this line. Okay, that is an open spot in the graph. And that's described right here. That means it is continuous only on the interval from negative infinity to 3. Notice the parentheses means that 3 is not included in this interval. And the interval positive 3 to positive infinity, once again, there is no square bracket here. It is a parenthesis. So that means positive 3 is not included in this part of the interval either. So it has a point of discontinuity at x is equal to 3. So it is only continuous over these two intervals. And then the last one is continuous all the way until you hit this vertical asymptote at -2. So you can say that there's a vertical asymptote that x is equal to -2, and it has an interval very similar to figure number 3 right there, where it goes from, it's continuous over the interval -infinity to -2. Once again, that's a parenthesis. And then it goes from -2 to positive infinity, parenthesis, no square brackets, because -2 is not included in either one of these intervals. Okay, so that's the first way we can describe the graph of a function as to whether it is continuous or it is not continuous, and we can describe the interval over which those occur. The next way that we can describe a function is by saying that it is either increasing, decreasing, or constant. Constant just means that it is not changing. I would hope that everybody knows that increase means that it is moving upward or rising. Decreasing something means it's going down. And just like we talked about earlier in the semester, we work in math usually left to right, even on graphs. So you need to be looking from the left side of your graph to the right side. If your graph is going upward, that means it is increasing. That means it has to be rising. Okay? Which means whichever your first x is, which is further to the left, when you compare it to your next x, which is the second x, further to the right, the first x has to be less than the second x. And if you know what f of x is, in order to plug those x's in, when you plug the first x in to your function, and you get a value here, and then you take your second x and plug it into your function, and you get a second value, well, the first value for f of x, which could be replaced with a y, also has to be less than the second value that you plug into f of x, which is the second y value. Okay, so you have to make sure that both the first x is less than the second x, and the first y is less than the second y. If that is true, then your function is increasing, and you can tell me where that increase starts and where that increase stops, and do it in very similar notation to what we saw in the book by giving me an interval. From where to where are you increasing along that function or along that graph? To decrease means you're falling from left to right. And you can describe that interval very similar. Your first x, which is furthest to the left, has to be greater than the second x. And when you plug those two x values in, the first answer you get for your function has to be greater than the second answer that you get for your function. So your y1 has to also be greater than your y2. Okay, both of these things have to be true. If they are, then it's decreasing. And once again, you can give that interval in interval notation about how far does it decrease, from what x to what x. And then if it's constant, then that means no matter what x you plug in, okay, whatever x you plug in, it doesn't matter what it is, your answer in your function will remain the same. The y values are not changing. And when y values do not change, even if your x's do, that creates a horizontal line when you work from left to right. And once again, you can say that a function is constant along an interval and give it to me in interval notation. So the notes say, see page 90, figure number 6. Those of you who don't have textbooks, here is page 90, figure 6. Here, your function is increasing. you can compare this x1 value to this x2 value, and x1 is less than x2. And at the same time, if you plug this x1 in, you get a y1 value. When you plug the x2 in, you get a y2 value, and this y1 is less than this y2. That means that this function right here is increasing along this interval. This is what it looks like to be decreasing. Once again, x1 is greater than your x2. Your y1 is also greater than your y2. Both of those things are true along this particular function or graph. So this graph is decreasing along this interval from here to here. And then horizontal flat line, no matter which x you put in, you get the same exact y values. Your y1 is equal to your y2. That means this function is constant along this interval. And you can see this quote right here goes right along with your notes. The great question to ask is, what does your y do as x goes from left to right? So you can go ahead and see that in your notes right here. Great question to ask to determine its behavior, whether it's increasing, decreasing, or constant, is to say, what is your y doing? Remember, y is your vertical going up and down. What is it doing as your x goes from the left side of your graph to the right side of your graph? And that will help you determine whether you are increasing, decreasing, or constant. Stay tuned for part 2.